Hi there, this is the second version then of the exercise 22D lesson video. We're going to extend what we did last time because we're now going to look at the hardest type of questions, which is this picture on I've got here where you have a ladder leaning against a wall. And of course the only thing that stops the ladder from sliding down, because its natural tendency is to want to fall down here and presumably fall down here. The only thing that can stop it doing that is a bit of friction. And here I've got friction acting on the floor at the base, and obviously it wants to slide this way, this ladder. So the friction therefore must oppose that motion. Now this is a simplified question because in reality you get friction on the wall as well, and the friction well, the ladder wants to fall this way, so the friction must go the other way. Usually you'd have a friction going there as well, but sometimes they simplify things and they'd say one of the walls is smooth, for instance. This must be a smooth wall. Can't get a smooth wall, of course, but there you go. So let's have a look at this. A reminder before I go any further, remember last time we were looking at resolving forces. So it must be a perpendicular force. There are other ways of talking about it, but that's the way I've described it. So that W at the moment, which goes straight down, is no good because it's not perpendicular to the rod. So what we try to do is we try to resolve that in that direction. And to do that we need this angle here, and then we do the we use cos for the adjacent force. Now I don't want this force in this direction, so effectively if you want the perpendicular force, as long as it's this angle here that you find, it will always be the sign that you use. Sometimes you might be told this angle instead, and if you use that angle, you'd use the cos. But as long as you use this angle, you'd use the sign. So let's try to practice that. Is this the same picture? It's not quite the same picture. Is it similar? Yeah, it's a 50 degree. Everything else looks the same. Is it identical? Yeah, it is. After all that, it was identical. The uniform ladder of length 6 meters. So we obviously know this is 3 meters either side of this because it says it's a uniform ladder. So therefore, the weight acts at the center. Hence, I can say 3 meters either side. And of mass 8, so this equals 8 times 9.8. My calculator out. 8 times 9.8 is 78.4. So just so we've got these things ready done, that's 78.4 newtons. It obviously says this is a 50 degree angle, and by alternate angles this is also 50 degrees up here. Just doing again a few more sums. That's that angle there because it's alternate to that. A smooth vertical wall, as I said, and a lower end on a rough horizontal ground. That's why we've got the friction here, because it's rough. Calculate both contact forces and the coefficient of friction. Okay, so let's go through this. First of all, the both contact forces stuff. Well, we've got two contact forces. There's one of them, the reaction that we get at the ground, and also with the reaction we get against the wall. The couple of things we can do straight away. We can say left equals right, and the only forces going left and right. And we've got the reaction at the wall must be equal to the friction. So if I get one of them, I get both of them. And the second thing, I can say up equals down, and what forces are going up? Rg is going up, and in fact there's only one force going down, that's the weight. So immediately I know that Rg must be equal to that 78.4 Newton force. So that one was relatively easy to find. Now I'm going to take moments. Now I don't know the friction. In fact I don't. I know Rg, but I'm going to take down here, I'll call it A. And this is B now up here. But I'm going to take moments at A. And that's because there's two forces there. I don't have to think about two forces there. Now, this is 3 away, but I'm going to need that perpendicular force. So that perpendicular force, as I've already mentioned in the introduction, I think that will be well, what was it? It was 78.4, but I've got to resolve it sine this angle here. And the nice thing is, just quite straightforwardly, if that's 50, that's a 90 degree angle, that must be 40. So 58 sine 40. 78.4 sine 40 times sine 40. I get 50.39. So I know that force now is 50.39. And so when I do it over here, I can say, from here, that 3 times by that perpendicular force. I suppose that will be a that will be an anti-clockwise force moment, whereas this one will make it go the other way. So yeah, I'm just getting my head around this. So the anti-clockwise equals clockwise rule that we've used in the past. I'm going to say it's 3 times by that 50.39 that we just calculated, and that's got to equal, now the second force is 6 away, times by the RW sine, and again notice what I'm doing, the RW is in the wrong direction, so I've got to resolve it in that direction, and I use the sine of that 50 to do that. So I can do the 6 sine 50. 6 times sine 50 is 4.59. So I've got 4.59, I'll put one more number, 6 RW. That's equal to this. So obviously RW is 3 times the 50 divided by the 4 and a bit. 3 times 50.39 divided by the last answer. And I get a slight rounding error potentially, but 32.9 newtons. So I've now worked out RW. Yep, done that. I've also worked out F by definition, because RW equals F. And I've got the two contact forces. The one thing I haven't yet got is the coefficient of friction between the ladder and the ground. And what you should remember, there is a simple rule. It says F equals mu R. And my F down here, my friction, was equal to RW, which is 32.9. And that equals mu. Mu is the coefficient of friction. You should have seen that before with Miss Fairvine. R is the reaction at the ground, obviously here, because that's where we're looking at. And Rg was equal to the weight, which is 78. So times 78.4. And that allows me just a simple division to work out mu. So that 32 and a bit divided by 78.4. I get 0.420 rounded to 3 sig figs. Again, possibility of rounding errors. Let's see what the answer actually says. 78.4, yep. 32.9, yep. And 0.420. There you are. So it all worked out in the end. That I like that. And the second and last example then is very similar. Looks almost identical, apart from now we haven't got the angle, and the weight has changed here. There's still no friction here. It's just slightly gone too high, but you get the idea that you've got this weight going across, and there's no friction here. It's a smooth. So it's a length 4, and it's uniform again. So I can write that. So uniform length 4. That's 12g. That's its weight. So 12 times by 9.8 is 117.6. Okay. So the only thing here is a backward one, because I've got to work backwards because I don't know what theta is. So let's try up equals down and things like that. Left equals right. First of all, I'll do. So I've got RW is equal to the friction. Up equals down. I've got the RG equals 117.6. So that's given me the same information as last time, just different numbers. And then again, last time I took moments here, I might as well do the same thing. So moments at A, I called this A last time, and up here was B. So moments from there was, if you remember, I had to do that. Now, last time I did say to you that this was 90 minus what the angle was. It was 50, so it was 40. That's 90 minus theta. Now it's not very nice using that, so it might be better on this example to use theta there. But when I use theta here, because of that, because I'm using the wrong angle, I have to use the wrong thing. So rather than using sine to get this perpendicular force, I'll end up using cos. So just be aware of that. What you should be aware of is that sine of 90 minus theta is actually the same as cos theta, which is why we can use the trick. So when I come over here, when I take moments, the first one is the 117.6 times by the force. What was the force? That is going to be 100 times by the cos of theta. That's what I meant to write. So that's me resolving it in this direction. That's the force. Don't forget the times by the distance, which is 2. And the same as last time, that's an anti-clockwise force. This is the clockwise, I should say moment. Anti-clockwise, of course, is equal to clockwise. And therefore, for the top one, the only one left, this one up here, that's 4 away. And what's the angle? Well, it's the RW. And again, that's theta there, because of alternate angles. And so I think it's quite obviously times by sine theta that I do have the proper angle to resolve it in a perpendicular direction. So given all of that, you'll notice I've got sine and cos, and now cos can move over that way, which will give me sine theta over cos theta. The one thing I still haven't got, I'm just going to write this here, 117.6, cos is gone, times by 2, divided by 4, and also divided by this RW. So if I move these over, but I don't yet know what RW is, and I've got this complication of sine over cos. Well, sine over cos is easy, that's tan theta, that's eventually what I'm going to use. 117.6 times, let's do that sum, times the 2, divided by the 4, I get 58.8. So this is 58.8, still to be divided by RW. But of course RW is equal to the friction, and I can work that out. F equals mu r, because this time they tell me the coefficient of friction is 0.4. So that's 0.4 times the r, and in this case it means Rg, because that is acting at the ground. And this will tell me effectively what friction is, and because I know friction and RW are the same, it tells me that. So 0.4 times 117.6, and I get 47.04. So not only is friction equal to that, but it's also equal to RW. So tan theta therefore is equal to the 58.8 divided by the RW, 47.04, slightly more than 1, what is it, 58.8 divided by that answer, I get 5 over 4, 1.25. And so it's quite easy therefore to say that theta is the inverse tan of 1.25, inverse tan of 1.25, and I get 51.3 degrees. Theta is 51.3 degrees, into 3 significant figures, 51.3 degrees. So we've done them right. You're going to see a few questions like that. They are at the harder end, so if you struggle, ask for help. The questions then are on exercise 22D. Have a go at them, do as many as you can, and best of luck.